Welcome back to video number 78. This is Larry Benko W0QE, and this video should be of interest to everyone who owns a hobbyist or professional vector network analyzer, or VNA. All VNAs need to be calibrated, and this is usually done with precision or semi-precision open, short, and usually 50 ohm loads, which are used to establish a reference plane for the measurements. This topic begs at least two questions, but the most important are: how well will the user-built calibration loads perform? And how difficult or easy are they to construct? In order to show how well the loads that I built perform, I'm going to do two experiments. The first experiment is going to be a scan on my 4170, and the second one is going to be a scan on my 8753 HP analyzer. So to begin with on this one, what I did was, this has got an N connector on it. I used an N to SMA adapter, and it's a good quality adapter which has metal in here, so the reference plane doesn't change if I tighten it a little bit more or loosen it. And I used one of the two open short loads that come in the 85033D calibration kit. And this one, I made the same connector type as my loads were. The reason for doing all this is so when I disconnect, after I calibrate with the load to short and the open here, and I take this off and I connect my homemade loads on here, I want to be able to not have any adapters or anything else in the system. I may have a little bit difference in my reference plane due to where the actual reference plane is in this cal kit versus mine, but I can correct for that very, very easily. But I don't want anything else in the circuit that's going to mess things up. And that's the way people who try to make high-frequency measurements typically do. The fewer the adapters, the fewer the number of pieces of cable, the fewer everything, the better off you are. So I'm going to do this, calibrate this. I averaged each data point from 1 to 180 megahertz. I think I averaged 16 times. Then I took this off. I put my own loads on. I torqued all these too, by the way, with a torque wrench, so that they're all exactly the same tightness. And I measured an open, a load, and a short of my own making to see what the comparison was between the calibration and my own. I took that data and I looked at it in SimSmith. So what I did was this circuit. So I caled it with a cal kit, and I'm measuring the homemade open short loads. Now this is going to look, there's a little bit maybe odd to some people here, and there's a lot of stuff I've done here, but it's pretty straightforward. The first thing I did is I have a load. In SimSmith, you can change the names of all these things. So to make this a little bit more descriptive, I called this one open. I loaded the file that was representative of the open. This one's short. I loaded the file representative of the short. I named this one 50, and you cannot put numbers to start the names up here. So I just did it 50 with letters rather than numbers. And this is the 50 ohm scan from the 4170. And what I expect to see, and let me change the reference plane here to 0. What I see is, let me get it off. Let me make it off a little bit. So what you see is I put a different piece of transmission line in each one of those, but this circuit right here sets the length to be the same in all cases. So I have the same piece of transmission line in each one of these scanned data sets from the 4170, and I'm trying to find a place where open everywhere, 50 ohms everywhere, and short everywhere. So what I'm going to do here is I'm going to change the length of this, and you can see the rotation you get when the reference plane is not what you expect it to be. And you can do whatever numbers you think you would like to see here. And you can zoom in on these and see how good they are. But pretty much minus 0.14 centimeters was what I concluded to be the best average. So the difference between the calibration plane and my loads was minus 0.14 centimeters. Now, there's no reason for that to be 0. It just is what it is. So my loads look pretty darn good here. If we look at the 50 ohm load scanned, I'm zooming in a lot here, and there's hardly anything going on at all. This is incredibly good. If I want to look at the 50 ohm SWR, I can look at the 50 ohm SWR here. Less than 1.005 up to 180 megahertz. So, it's what you would call amazingly good. And I wrote some other stuff here to basically let me look at the magnitude of the impedance if I wanted to look at it. And things like that. But the idea was to do the best job I could do at getting the same line extension for all three loads to give me a good answer. And this indicates that my loads are pretty darn good. Then I took this exact same circuit here and I did it opposite. I calibrated the 4170 with my homemade cal kit and I measured with the HP open short load. So I was measuring the HP open short load after I calibrated my homemade kit. I would expect to see the inverse of this. So remember that this one is at minus 0.14 centimeters. This one, when I do it, comes out to be 0.12 centimeters. Not exactly the same. The ambiguity between the two of those is 0.02 centimeters. 0.02 centimeters is about 0.008 of an inch, 0.008 inches. So I have a disparity in my loads of that amount. Or maybe I don't. There's a couple things come to mind when you start to look at this, and that is that the cal kit that I have, my HP cal kit, is not necessarily perfect. What is perfect, or almost perfect, is my HP cal kit in combination with my HP analyzer. If there was some little error in the cal kit, the analyzer knows about the cal kit I'm using, so it can correct for that. So this isn't a definitive test by any means, but what it is an interesting way to be able to look at what you've got and compare things in SimSmith. I can't get the data out of my large analyzer easily into SimSmith. I can get it out. It's very painful, so I didn't do it. But what you have is the ability to view what you've got is not nearly as good as what I have in SimSmith. Let's go on and look at that experiment now. And for the final experiment, I took my 8753 analyzer and I swept it from 300 kilohertz to 3 gigahertz. I calibrated it with the same HP 85033D load that I used before on the 4170, except in this case, the analyzer knew about that load. It knew exactly all its characteristics and it knew its weaknesses and it knew how to compensate for it. So I used that load, I calibrated it, and then I put in my own loads and measured the values of them. Now I would have expected to see the short be a dot here, the load to be a dot in the center, and the open to be a dot here. After adjusting for the delay, and this analyzer adjusts in picoseconds, it turns out that both this arc that you get here from 300 kilohertz down to 3 gigahertz is slightly capacitive. Turns out the open is slightly capacitive too. What that means is to get the open to be perfect, I needed a 47.24 picosecond delay. To get the short to be perfect, I needed it to be a 43.896 picosecond delay, or an average of 45.57, which is what I set for these two plots. Now that means the short, as you go up to 3 gigahertz, starts to look a little teeny bit capacitive, and open at 3 gigahertz looks a little bit teeny bit capacitive also. The error, if you calculate what that means in inches with a velocity factor of 0.695, is 0.026, 26 thousandths of an inch error. The 4170 showed an error of about 8 thousandths of an inch. So I think the problem is with my open. The opens are notoriously hard to make accurate because of fringing capacitance and things like that. But nevertheless, if this is all you get at 3 gigahertz, remember at 1 gigahertz you only get 1/3 of that rotation. So it's really almost insignificant. On the other hand, the 50 ohm load, I didn't plot it. It looked like a dot in the middle, no matter what the delay is. But I did measure SWR. From 300 kilohertz to 3 gigahertz, with this being the baseline 0 right here, with the little arrow there. The SWR at 200 megahertz was 1.0019. At 2 gigahertz, it was 1.0. 1 gigahertz, it was 1.0031, and at 3 gigahertz, it was 1.0071, which is amazingly good for the 50 ohm load. Now, this isn't perfect, but in my case here, I matched my two resistors in my original load. They were two resistors were in parallel. I matched them with a multimeter that was very accurate for a 4-lead multimeter, and I measured the two resistances and I picked values so that when they were in parallel, I got exactly 50 ohms. And I think my load is like 50.0013, and the HP load is like 50.007 or something. So they're extremely close, which is why I get such a good SWR. But the fact that it's very, very flat also is a good testament to the fact that the load is quite good. And as an added bonus, I decided to take the existing test setup I just used a moment ago and insert two adapters whose net effect would be 0. So I went from a SMA female to male here. So this looked like what the analyzer looked like before, and this looked like what the load looked like before. So I could just plug this into my analyzer and then plug my 50 ohm load into here, and I could see the effect, SWR effect of these two adapters. And this is an N connector in the middle, an N male and an N female. And before we had an SWR of 1.007 to 1, and now the SWR has risen to 1.05 to 1. So 1.007 to 1.05. This is still a good SWR, but there's definitely an effect due to these adapters. And these are incredibly good, high-quality adapters. I did the same thing with B and C. The male was on this side, the female was on this side. Didn't really make much difference. And or it shouldn't make much difference. And again, the SMA females here, the SMA males here, the load was out here, the analyzer was over here, and now the SWR has risen to 1.15 to 1 from 1.007. And it looks like a lot of difference. It just happens to be the scale's incredibly magnified. But nevertheless, the effect of the adapters is not positive. I think we knew it wasn't going to be it was going to be a detriment. And the problem we have with adapters is these are probably about as good a quality adapters as you can get, other than maybe some metrology type adapters. And because of that, typical adapters will be much worse. Anytime you're operating at high frequency and you're trying to make accurate measurements, most people in industry typically use a cal kit that is of the same connector type that they're going to use for their final measurements. So you don't need to have any adapters in your system. Or if you have them before where they get calibrated out. The N connector here is a rigid connector. This being not so rigid is what I attribute the higher SWR to be. But again, I don't know really for sure. We know one of these could be 90% of the error and one could be only 10%, or vice versa. I don't know that. But anyways, let's go on and look at what it takes to actually build the loads. Shown in the first picture are three different types of loads that I built. SMA female, N female, B and C female. All these connectors had captive center pins which did not move at all, allowing me to solder very small resistors on there onto the center pin and not have to worry about breaking the resistor as the connector was plugged in or not. Also, all the loads were done with two 100 ohm resistors in parallel. And that was due to some work I had done earlier. Here's a graph that shows, this graph came from a friend of mine in France who works for CERN, and he was doing some work for something else. But anyways, he measured a bunch of surface mount components. At the same time I did the same test, and we sort of crossed paths. And I've got a SimSmith graph here that's circuit that shows the same thing. What I've got is a circuit here that is a single resistor in a 50 ohm structure. So as the resistor gets to be large, you'll see attenuation, but the attenuation versus frequency decreases. And it decreases due to this parallel capacitance. It increases at the low resistance values due to excess inductance relative to the capacitance, but at high frequencies the capacitance dominates. And this capacitance turns out to be, since it's all asymptotic along this line here, if you calculate what that line is, in his case it was 50 femtofarads, which is interesting because I didn't quite come up with that value. I came up with 55, but that's pretty close. What we see here is that This line right here is for a 100 ohm resistor. We see a very, very flat frequency response. This line right here is for a 316 ohm resistor. He did 100, 330, 1K. I did 100, 316, 1K. The reason mine are geometrically spaced, his was the standard values. But we see that the 300 ohm resistor starts to have some slope here where the 100 ohm does not. So if you build this circuit with two 100 ohm resistors, you'll get a flatter frequency response than if you had built it with a single 50, which would be up here somewhere. And down here would be four 100 ohm resistors, four 200 ohm resistors, which would give you worse performance too. The two 100s gave the best performance. So looking at more connectors, again, all these have captive pins. This one is out of focus, I mentioned in the previous video. It's an N connector, a two-part N connector with the center pin fixed. And I drilled these holes out and I soldered the open, short, and load aspects inside of here by going into the side with a small soldering iron. This is an Esso 239 connector, Teflon based, again, very rigid center pin. I believe these were bought at HRO here in the States. This connector is an N male connector, which is shown here. Again, a captive center pin, a fairly flat area here. And these connectors are a little tricky to solder. They're kind of, they got a plating on them that doesn't take solder real well. So what I do is I put acid-based flux on here. I get a spot that solders, and then I wick all the solder off, and then rosin-based solder will solder on here just fine. But all these show a solder blob. This is the exact connector I use for the N female connector, the N female loads I did. This is what I did for some N male loads, which are not shown. I have not built any UHF connector loads, but this would work fine for a female load. And by the way, the female loads I use more often than the male loads. And the reason for that is I can put them on the end of the connector where I have a male connector coming in. I put the open short load there, and then when I remove it, I can plug that connector that I had, which is a male, into the device under test, which usually has a female connector. Here's some more connectors. These are SMAs. These, I've picked up a whole bunch of these at a ham fest a while back. These have a piece of Teflon that comes out, but you can take a hobby knife and scrape and cut it. And if you cut it without cutting through the center pin, you end up with a connector that looks like this, very flat again. And these were pretty cheap. I mean, I think I got 100 of them for, I don't know what it was, like 25 bucks or something from this guy. This is not a good example. This one is not a flat bottom. You'd have to put the resistors standing on their end. That does not seem to be nearly as good as having the resistors flat. This one, if you ground the little pins off, you'll be flat too. Here's an example of a really bad N-male load set. We've got the open with nothing done to it, but you see a pin there where this was an SMA to N-male, and they just put a little piece of string tubing around here. But the reference plane is down about 1/8 of an inch from the end. Here, what they did over here was they put a wire in here. They soldered it, stuck it up, and then soldered a piece of something over on top of here. So this one's the reference plane for this one is at the top here. The reference plane for this one's down 1/8 of an inch, and then they put a resistor in series with the center pin somehow down in here. I don't know what the resistor is, but this was just absolutely terrible, and it was pretty bad over the high HF range. You could get away with this, would be okay at the low HF range, maybe up through 20 or 30 megahertz, but beyond that, it wasn't very good. And there's no reason to spend your time doing this when you can do something a little bit better. You do have to, unfortunately, notice these connector types are not even the same connector type. These two are the same connector type. This is a different connector type. You end up, when you do this kind of stuff, I'd make all the connectors identical. They don't have to be the same connectors I use. The ones I use, I'd like to be able to give everybody part numbers on them, but there's stuff I had just laying around that I had obtained over the years. And as most people know, if you're in the industry doing this kind of stuff, over time you end up with, you start to accumulate stuff, and stuff's good stuff. And when the good stuff shows up, you avail yourself of it, and you buy it, and then you use it at a later point in time. And to finish things up, here's a slide I showed earlier. This group of components right here represents an open short load with a BNC male to banana plug, a short, a load, two small 100 ohm resistors on a thin circuit board. There's the reference plane. And I've made a lot of open wire transmission line measurements with a adapter such as this. Here's another adapter I built. This one has 4 little screw terminals that are about 1/8 of an inch high. It calibrates with a 49.94 ohm resistor right there, a short that can be put in those 2 holes, and then the open is nothing, of course. You can turn it over, and there's a couple little screw machine sockets on the back, which I use to make crystal measurements. It's been very useful. It's good throughout the HF range and most of the VHF range pretty easily. These I mentioned in the previous video on the reference plane. They do not need to have captive pins. You don't have any small components that are soldered here that you're in danger of breaking. As you do these things and you make more adapters, you find the usefulness in them. The ability, obviously, is to be able to make better measurements quicker, more competently, and feel comfortable in making those measurements. So to summarize this, if I was going to build more open short loads, I would demand every single time I did it, identical connectors for a given load type, captive center pin, Teflon only insulation. When you start soldering on these, if they have Delrin insulation in them, you're going to have a mess. Plus, the Teflon maintains a better 50 ohm structure through here, which means it's easier to do line extension and things like that. And I would make sure my soldering skills were good. I'd have fun. Also, if you have a friend or friends who are into these kinds of hobbies, compare what you've got to what they've got. You can take their calibration loads and compare, and then do like I did in the first experiment today. Use their cal kit and then measure your cal kit with it afterward, and you can find out how close they are together. And between the two of you, or the group of you, you're able to increase your competencies. Hope everyone's enjoyed this video. If you have, please give me a thumbs up. Also, if you have any comments, let me know. If you think you can do better than I have, please do. Let me know when you're done. Let me know what kind of tests you did. I would certainly be glad to publish something that was better than what I've done. Thank you again.